X-ray equipment that can take up an entire room could be made more compact thanks to the work of an A-star researcher and his collaborators. Liang Jia Wang of the Singapore Institute of Manufacturing Technology and colleagues have discovered how to design surfaces to take in light and pump out X-rays by patterning them with a nanoscale precision. The research was done in collaboration with 𝘍𝘏𝘯𝘕 Sojuchek and Nicholas Rivera of MIT, Ido Kamenur of Technion, and Bjorn Maas of the University of Mons. This is St. Paul's Cathedral in London. Inside this grand structure lies one fascinating quirk. A cup deer on one end of this gallery can pick up a whisper from the opposite side. Called a whispering gallery, it's a phenomenon that's been replicated in dome structures around the world. Now imagine for a second that as it skips along the walls, the whisper becomes a high-pitched sound. That's essentially what the researchers have done, only with waves of light instead of sound. Through computer simulations, the team discovered that specially patterned silver or graphene surfaces, also called metasurfaces, can transform light into sources of X-rays. The unique properties of silver and graphene enable them to interact strongly with light of a certain wavelength, UV for silver and infrared for graphene. Much like the Whispering Gallery in St. Paul's Cathedral, the key to sculpting incoming waves lies in getting the right geometry. The team riddled their virtual surfaces with periodic structures, nearly 10 times smaller than the wavelength of the incoming light. By adding a stream of high-energy electrons, the researchers showed that strong electromagnetic coupling to their metasurface could yield X-rays from pulses of simple laser light. More importantly, they showed that the strength of those X-rays could be modified by tweaking the geometry of their setup, such as the angle at which the laser pulses are delivered and the spacing and size of the metasurface patterns. The intensity of the resulting X-rays are on par with those emitted by common X-ray tubes, but at a fraction of the size, the specially designed metasurfaces could make for much smaller diagnostic equipment. By exploring the unique tunability of graphene and other exotic materials, the team hopes to develop X-ray generating metasurfaces with even greater versatility.